Now let's discuss about the working condition of the transformer when the load is not connected, that means no load condition, and when the load is connected, that means on load condition. So here we can see the transformer is secondary terminal is open circuited, and when we are giving primary voltage VP, some I naught is the current draws from the primary side, that may be no load current, that is called no load current I naught. When the transformer is on no load condition, this I naught no load condition is having two components. One is magnetizing component Im or I mu, and the second one is the working component IW. So the no load current is having two components. One is magnetizing component, is called magnetizing component, and this is called working component. So when the secondary terminal is open circuited, only small amount of current is drawn from the supply. So here the magnetizing current is responsible to generate the flux in the core, and this working component IW is responsible to overcome that losses, no load losses, that is hysteresis losses and eddy current losses. Those are called iron losses. So magnetic core లో ఏవైతే లాసెస్ ఉంటాయో ఐరన్ లాసెస్ ని ఓవర్కమ్ చేయడానికి, అవి విత్స్టాండ్ చేయడానికి వర్కింగ్ కాంపోనెంట్ అనేది యూజ్ అవుతుంది. దెన్ మ్యాగ్నెటైజింగ్ కాంపోనెంట్ ఈజ్ రెస్పాన్సిబుల్ ఫర్ జనరేటింగ్ ద ఫ్లక్స్. లెట్స్ సీ ఇన్ ద నెక్స్ట్ స్లైడ్. So when the practical transformer is on no load condition, the magnetizing component Im, which is responsible for the production of flux in the core. So it is also called reactive or wattless compound. And the power component or working component IC, sometimes it will be represented as IC or sometimes it will be represented IW, which will supply the total losses, hysteresis and eddy current losses, and it is also known as active and wattful component. So that is wattless component, it will be the wattful component. So these are the vectors. So I can write I naught is equal to I mu plus I double. So when I writing in the magnitude, I naught square is equal to Im square plus Ic square. If I draw a phasor diagram when the transformer is on no load condition, so I take it as a flux as a reference, flux phi as a reference. So this flux is due to the magnetizing component. So this magnetizing component is in phase with the flux. Why? Because Im is responsible for production of flux or I mu. So this is the in phase, that means the phase angle between flux and magnetizing component is 0, and the working component is in phase 90 degrees with the magnetizing component, that is working component. This will be 90 degrees. The resultant of these two, the vector sum of these magnetizing component I mu and working component IW, is totally called as a no load current, that can be represented as this way. This is I naught. So this is vector sum. Now this I naught and this V1, the phase angle between V1 and I naught is nothing but no load power angle, phi naught, From this diagram we can mention IW as I naught cos phi naught. Yes, from this. So from this right angle triangle, if I make cos phi naught, that is Im by hypotenuse I naught. In the similar way, cos sin phi naught is Ic by I naught. Okay, these are all mathematics you can understand well. So I naught square is equal to Im square plus Ic square, and one is magnetizing compound and another one is a working compound. So the phase angle between I naught and V naught is phi naught. That is, we can take no load power factor is cos phi naught. No load power factor we can mention as cos phi naught. This value will be very less. Now the second condition, when the transformer is on load condition. The transformer is on load condition. So this is the diagram we can use for our transformer on load. Load means then the secondary terminal is connected to some load, whether it may be bulb. So whatever the load is connected is, it's like a consumer. It's a consumer. So whenever the load is connected here, some current, secondary current Is will flow through the load. So here we have to understand, when the secondary current I2 or Is set up own flux in the secondary side. So current ఇలా flow అవుతున్నప్పుడు the flux will set up. So from here we can understand, when the load is connected, the secondary side the current will flow through the load. Whenever the current I2 set up its own flux in the secondary winding, it will definitely opposite to the main flux, or it will weakens the main flux. Why? Because due to this flux, EMF E2 is generated. Because of E2 and load connected, the I2 current will flow through the load. According to Lenz's law, effect always opposes the cause. This current will produce its own flux, which will opposite to the main flux. Suppose when the load is not connected, some phi naught is flowing through this secondary winding. If the load is connected, some opposing flux will be generated, that will be taken as phi 2, and it will oppose the main flux, so that the EMF at primary side will be reduced. So if the flux is weakens or reduced, automatically the induced EMF at primary side is also reduced. If the E1 is reduced and V1 is maintained as constant, then the additional current will flow from the primary side. So initially there is a no load current I naught, plus when the E1 is reduced, some additional current will flow to compensate this flux to maintain constant. సో ఇక్కడ ఎంత కరెంట్ డ్రా చేస్తుంది అంటే, వాట్ ఎవర్ ద ఫ్లక్స్ ఈజ్ వీకెండ్స్ ఆర్ ఎంతైతే ఫ్లక్స్ ఇక్కడ రెడ్యూస్ అయిందో, ద సేమ్ అమౌంట్ ఆఫ్ ఫ్లక్స్ విల్ బి recreated or generated with additional current, that is I1 dash. It is very important. When the transformer is connected on load, the secondary terminal current I2 current will flow through the load, and I2 will produce its own flux, which will opposite to the main flux, and flux will be weakens. So the flux in the core will be reduced momentarily. If the flux is reduced, automatically primary side induced EMF is also reduced, E1 reduced. If the E1 is reduced and voltage V1 is maintained constant supply, then what will happen to compensate the reduced magnetic flux? Some additional amount of current is drawn from the primary side, that will be I1 dash. How much amount of current will be drawn from the primary side? Means it has to supply whatever the amount of flux is reduced due to the I2. So it is very important. If you see here, the secondary current I2 set up its own flux, phi 2 opposing the main no load flux phi naught. Phi 2 weakens the primary flux phi naught, leads to reduction of E1 magnitude, and V1 gains the upper hand over E1 and causes more current flow in the primary. Okay, so So here we have to understand whatever the load condition, the net flux passing through the core approximately same. So initially I mentioned the transformer is a constant flux device. So whether the load is connected or no load is connected, so inductive load is there or capacitive load is there or resistive load is there, whatever the load, the flux flowing through the iron core will be constant. That's why a transformer is also known as a constant flux device. If the load is connected, because of I2, some opposite flux will be there, then the flux reduced or main flux in the core will be reduced. If the flux is reduced, automatically primary side EMF is reduced so that it will draw more current from the primary to compensate that reduction of the flux to maintain the flux constant in the core. Best operation of the transformer when the load is connected. So that's why I can say transformer is a static device. Transformer is a constant flux device, constant power device, and constant frequency device. This is a very important. And here we can say the phasor diagram for the inductive load is mentioned. I can take it as here also phi as the reference, and this is the no load current initially, no load current. And if the amount of current from the primary, here they mentioned as I2 dash. Why? Because of I2 some amount of current is drawn from the primary, that's why they mentioned as I2 dash. Now here I mentioned as I1 dash, no problem, whatever it is symbol you can mention, it is I2 dash. Now the total current, so I0 plus I1 dash is nothing but total primary current, so this is called total I1. Now I1 is equal to, so vector sum I0 plus I1 dash, sometimes it can be represent I2 dash. Okay, so these are the vector sum of these two can be represented as total primary current I1. You can say it is lagging load, inductive load, that's why V1 and I1 are in lagging with the power factor 5. In the similar way I2 and E2 are in lagging condition with the theta, with an angle theta 2. So it is very easy to understand. When the load is connected, the flux in the main core will be reduced. Because of reduction in the flux, the induced EMF in the primary side is also reduced, and V1 will becomes the upper hand. So it will draw the more current from the primary side to compensate the reduction of the flux. So this is the vector diagram. When you take it as a resistive load, so this is the diagram given for resistive load. When the resistive load phi1 is also 0, so phi2 is 0. Phi2 is 0. Why? Because E2 in phase with I2. In phase with I2, that is phi2 is equal to 0 for resistive load. So you can mention I2 in phase with the I2. Okay, but this is purpose of resistive load. And I2 dash in phase with the V1. I2 dash in phase with the V1. Why? Because I2 dash is because of current I2. Because of current I2, I2 is related to resistive load. So because of I2, some more current is drawn from the primary side, that is I2 dash. So in the previous I mentioned as I1 dash, they will mention as I2, no problem. The concept is same. So because of resistive load, some current is drawn from the primary, that should be in phase with the primary voltage. So you have to understand this concept. Okay. And these are the simple numericals we have here. So I can solve this third problem. 1300 volts by 300 volts single phase transformer gives 0.6 amperes and 60 watts as a wattmeter readings when the supply is given to low voltage winding is kept open. So when supply is given to low voltage winding, here some they didn't mention, and high voltage winding is kept open. Then find power factor of no load current. Now we can understand P naught. So the given P naught no load voltage is 60 watts, and I1 current, I naught current, no load current, that is 0.6 amperes. We already know P naught is equal to V naught I naught cos phi naught. So 60 is equal to, so no load voltage, you can have primary side, it is 300 volts into I naught is 0.6 amperes into cos phi naught. Now the power factor of cos phi naught is equal to 0.33. So it is inductive load, that is lag. So 330 side voltage, so you can understand, so I will draw diagram here. So if it is a transformer, so this is 3300 volts and this is 300 volts. So when it is no load connected, so the sum of current is flowing, it is I naught. So the power P naught is equal to V naught I naught. We calculate the power factor. And next, the magnetizing component Im is equal to, we already know, I naught sin phi naught is for magnetizing component. So cos phi naught we calculated. So from this we can calculate I naught into square root of 1 minus cos square phi naught. Im component 0.566 amperes. Now iron loss component I working is equal to I naught cos phi naught. I naught is 0.6 into cos phi naught is 0.33. Now it is 0.198. So with this we can solve any problem. So these are the basic idea transformer on load condition, on no load condition. Right? Thank you.